Okay, so what we're going to be going over today, guys, is this lab here, Science 10 Measuring Kinetic and Potential Energy Lab. All right, now looking at the diagram there sets up very much like the work lab. Okay, you're going to have a spring scale, you're going to have a rubber band, set between the legs of two desks. All right, how are we going to measure the potential energy disposed in that rubber band? Okay, we're going to use the spring scale, and what else? The spring scale will tell us what? The force. What else do we need to know the potential energy in the rubber band? How far we pull it back. All right, so that part from the work lab, exactly the same. The work we do using the spring scale to pull back that rubber band is going to be the potential energy stored in the rubber band. All right, we'll have that. What we want to find out is how much of that potential energy actually gets converted into kinetic energy for the little cart that we're going to shoot out. All right, now, are there lots of places for this cart and this rubber band system to lose energy? Yes. Okay. There's all kinds of work that's going to be done against what we call non-conservative forces. All right. They're the ones that make it look like the law of conservation of energy doesn't apply. Okay. It does. All that work is still in the system. It's just not doing useful work anymore. It becomes sound or it becomes heat or whatever. Okay. Everybody follow me there? All right. So that's kind of what we're going to be doing here. We can calculate the potential energy by figuring out how much work we do in pulling back the rubber band. Okay, so we're looking at how much of the available potential energy is converted to kinetic, in a mechanical energy conversion. Okay, we want to identify the manipulated, responding, and controlled variables. Okay, so in the procedure here, so we'll outline the procedure and then we'll look at what those variables might be. Okay, so we're going to attach the rubber band, same as we did before. Use the spring scale to draw back the elastic to a chosen distance and record the force required to do this. Place the Hall's carriage. Okay, a Hall's carriage doesn't look quite like the little Tinker Toy block thing they've got in that. This is a Hall's carriage. Okay. The reason we use these ones is they tend to usually, if you do it right, they go in a straight line pretty well. All right. If you get them in there crooked, they will spin out. Okay. Which, although looks cool, doesn't give you very good results. Okay. So it's going to take a little while to get the hang of how to shoot these things nice and straight. Right. The other advantage of them is their wheels are not nearly as frictionless as the other carts, and as a result, we can do them in this room and not have to worry about them hitting walls and getting broken. Okay, like we do with the fancy carts. All right, so we'll be using those. Okay, they work just great for this. All right, so we'll place the Hall's carriage in the rubber band, pull it back. Okay, have a timer. Cue the person holding the rubber band to release the system and start timing. Here's the reason we want to do that. We're going to use an acceleration formula in this lab that we don't actually use for anything else in Science 10. All right? The reason we want to do that is because we don't know the initial velocity of the cart. There's no way for us to find that out or measure that in this lab. So what we have to do instead is use the distance traveled by the cart to figure out what its initial velocity would be. All right. Now the formula is outlined for you in here, okay, and you'll be able to do that relatively easily. Okay, I'll show it to you and everything here. All right, it's actually in step 2A here in the initiating and planning. I'll go over it in a minute. That'll help us to determine what the initial velocity of the cart was. Is that important? Yeah, because that tells us essentially the maximum energy of the cart. Okay, things like that. So what we'll use that formula for is to determine the acceleration. Then we'll find the force using F equals ma. That other formula that I told you we'll only use one time. Today's the day. Okay, today's the day we use that other formula. Okay, and then we'll measure the distance the cart travels. Then we can use the force and the distance that the cart travels to determine how much work was done in slowing it down. Everybody follow me? Okay, so we're going to find the work that was done by us stretching the rubber band, and then the work done by friction in slowing the car down, okay, until it comes to a stop. All right. Ideally, those two numbers should be close. Okay. They might not be. That's okay if they're not. Okay. Part of the lab is to determine how efficient is an energy conversion, how much of it actually gets put into where we want it to go. All right. Everyone sort of following me there? All right, so you'll have the timer. Okay, measure and record how far the cart traveled from the legs of the desk. Do 3 more trials and average your times and distances. Okay, create a chart to hold all the necessary results and observations you'll record. All right, so we'll go back here to initiating and planning because this talks about the things that we're going to have to record. All right, so there are several variables you need to record in this lab in order to calculate the energies. Potential energy. Now, if we're determining how far back to pull the rubber band, are we deciding how much potential energy is available in this lab? Yes, we are. Okay? So the manipulated variable in this lab is the potential energy. Okay? Because it's related to the work we do. Okay. The kinetic energy, okay, has to do with the mass of the cart, the distance traveled by the cart, okay, and final velocity, 0, time of travel, all of that kind of stuff. Okay? That is hopefully going to be our responding variable. Okay, it's the thing that we hope will be affected by the potential energy. Okay, controlled variables, a lot of them the same as the last time. Yeah, a lot of them will be the same as the work lab. There's a few new ones. Okay, obviously some of the equipment you use should probably remain the same throughout the entire lab. Okay. All right, values you're going to need to calculate. So these 2 things definitely need to be in your chart. Agreed? Okay, so potential and kinetic energy, you'll need to have a spot in your chart for those. Okay, things you're going to have to calculate. Are you going to need to show me these calculations? Yes. Okay, acceleration of the cart. All right, so to determine the acceleration of the cart, we're going to use this formula right here. Acceleration equals 2 times the distance divided by t squared. All right, that will give us the acceleration of the cart. Okay, the kinetic energy, and as I said to you before, friction is going to do all the work on the cart in slowing it down. All right, to determine the kinetic energy, okay, we're going to use the fact that all of the kinetic energy the cart had will be taken away by the force of friction. Okay, the force of friction will do work on the cart. How much work? However much energy the cart had to begin with. Agreed? Because if it comes to a stop, what's its final energy? 0. So the work done against friction is equal to the initial kinetic energy of the cart. Does that make sense? Right? Because its energy, work is a change in energy. Okay, we've been going over that. Its energy changes from whatever value it had at the beginning to 0. All right? So we're saying that EK equals the work, okay, and that means force times distance. How come it's written as MAD here? Mass times acceleration times distance. Okay, that's this formula here. That's on your formula sheet, F equals ma. It's Newton's second law. Not that you ever need to know that until Physics 20, okay? But that's what it is. So, is MAD the same as this? Yes. Okay? MAD is the same as FD. All right? Just another way of writing it. All right, so we'll calculate kinetic energy for each trial by taking the acceleration that we calculate this way and multiplying it, okay, in this formula here, mass times acceleration times distance. Right? Nothing terribly difficult, just all multiplication stuff. Okay? Then the potential energy, okay, minus our kinetic energy, okay, should equal that. All right? Everybody follow me there? All right. So in the analysis here, it's asking you to do a lot of the stuff it's explaining up here in the initiating and planning. So calculate the work done in pulling back the rubber band. Show your work. Okay, that a relatively easy calculation. Okay, calculate the acceleration of the cart using this formula. All right, so show me your calculations. Calculate the kinetic energy doing this. All right, and then outline how you determined the potential and kinetic energies of the system. That's what we just talked about. How did we know what the potential energy was? How did we get it? How did we determine what the potential energy of the cart was? What force did we use to determine that? Okay, it's all stated back in here. You basically just have to look back in here to get those answers. Okay, and then for 5, did the potential energy of the system equal the system's kinetic energy? Why or why not? Okay, suggest reasons why. Okay, and then you have a conclusion, evaluation, same as always. You don't have to do the class discussion stuff. Okay. So let's go back up here because we talked about the design, but we didn't talk about the hypothesis. Okay, generate a hypothesis that's a tentative answer to the problem. Explain why this is so. So if, and then. Okay, The if part, okay, should talk about the perfect physical world relationship between the available potential energy and the amount of kinetic energy that would result. Okay? I think we all know what that relationship should be. Okay? In the and part, you talk about what we're doing here. In the then part, tell me your expected results. Okay? Everybody got it? All right. So, there's no graphs in this one. Okay? There's a bit of calculation, but it's all outlined for you. You don't have to think any of it up. Okay? Questions on that stuff? Okay, couple of tips for when you're shooting out the Hall's carriages here. All right. What you want to try and do is get the rubber band down here on the lower flat part, okay, of the cart. If you get it up here and you let it go, it just slides up. Okay, it just slides up the incline here. So you want to try and get, okay, the Hall's carriage in there. Now, other thing to recognize here, when you measure your potential energy with the spring scale. Okay, pull it back whatever distance you decide. Okay, pull it back a little ways, measure that, then get rid of the spring scale. You do not want the spring scale attached to the rubber band when you put the Hall's carriage in and pull it back to that same distance and let it go. Why? Yeah, it'll shoot the spring scale. Okay, I don't want any spring scales flying around taking out people's eyes. If they are still attached to the rubber band when you let the Hall's carriage go, not all of the work done is done on the Hall's carriage. Some of it will be done in propelling the spring scale at somebody. Okay, we don't want that. All right, so just do it. Pull it back. Decide what distance you're going to pull it back to. Pull it back to there. Measure the force. You're done with the spring scale. You don't need it again. Put the Hall's carriage in. Pull it back to the same distance. Everybody got it? Okay. Other recommendation. Pulling it back as far as possible isn't the best way to do this. There comes a point where you get so much tension in the rubber band that it snaps so hard it just flips the Hall's carriage over. All right? So, when you're pulling that back, pick an intermediate distance. We don't need a contest on who can shoot the car the farthest. We need good data. And that actually comes from a moderate amount of stretch, not an extreme amount of stretch. Okay? Questions on that, guys? Maddie? Yes, do 3 more trials and average your times and distances. So record your times and then just have an average underneath. So add them together, divide by 4. Okay? It eliminates a lot of the error because it doesn't shoot perfectly straight each time, and so we need to have some trials so we get a better idea of what the real value is. Okay? You're going to need some room. I would recommend using kind of the wider lanes that we have here in the room. You can work towards each other. If we have a group at the back there shooting towards the front, a group here shooting towards the back, okay, a group here and a group there shooting towards each other, these don't go far enough that they're likely to hit each other. Okay, they really don't. Now, when you're measuring, okay, I mean, we've got a lot of meter sticks, but chances are you're going to need more than one. Okay, or you're going to need to lay it down, mark on the floor, and then move it again. Everybody got me there? It's going to shoot probably more than a meter. Okay, and so you're going to need to make sure you're measuring correctly and as straight as possible. Do you have anything along the floor that can help you make sure you're measuring as straight as possible? Yes, tiles. Tiles can help you to keep the rulers relatively straight. Okay. Now, what if your car goes off to the side a little bit? Is that okay? It's fine. Okay? It is fine. Just measure straight. Okay? So you'll have to eyeball a little bit when you get up to the level of the cart. Okay? My recommendation would be to pull a mark on the floor. Erase it after. Don't leave it on the floor. Okay? Erase it after. But take a marker and just put little marks on the floor. Okay? Maybe do like all your trials, just mark trial 1. Okay, do the next one, then measure them all at one time. Save you a little bit of time that way. Okay? All right, have at her. Okay, if you're having this problem, your cart's going too far. if your cart is going too far, if you're having that problem, what's the solution? Right. Give it less potential energy, it'll have less kinetic energy, it won't go as far. i.e., don't pull it back so far. Okay? Just measure a different one. Don't pull it back quite so far. Okay, listen up here, guys. Quick thing here about your data. I don't really care what kind of chart you use for your data, okay? But you have to record the things it tells you to record, okay? Here's why. You need to have 4 different values for the distance traveled by your car. 4 different values for the time it took for it to travel that far. Okay? Then you're going to calculate the average of the distance and the time and use that average to calculate the acceleration of the cart. The average acceleration of the cart. You guys follow me there? Okay? So you don't need to calculate acceleration 4 times, okay? Average your distance and time, use the averages to calculate the average acceleration of the cart. Does everyone follow there? Okay? So, now, guys, things you're going to want to have in there. Okay? For your potential energy chart, if you have it this way, it doesn't matter if you do it this way or not. Okay? Force from the spring scale, distance, energy is force times distance. Okay? For your kinetic energy chart, okay, you're going to have the mass of your cart in kilograms, okay, the distance traveled by the cart on release. That could be, you might have 4 of those, or you might just put in the average, okay, something like that. Time traveled by the cart on release. You have 4 values for that. Give me the average, okay. Final speed is always 0, okay. And the kinetic energy is mass times acceleration times distance. That is calculated using average acceleration, average distance. Everybody follow? Okay, you don't need to do that calculation 4 times. Just use the averages to calculate that. It'll save you some work. All right, is that a little more clear on what I'm looking for data? Okay. Okay, so yeah, that should cover it there. Okay, I kind of built a different chart here. I was kind of toying with different ideas for charts, but you can do whatever chart you want. But I mean, you got to have this data. Okay, somewhere in some kind of chart, you've got to have the trial numbers, the distances traveled, the times it took, okay, a column or a row for the averages here, okay. Acceleration, you only need to calculate an average value, so you'd really only be doing this. Still show me a calculation of that somewhere, okay. For EP, you only really need to fill in the bottom one because it's the same for all of them. And EK, remember, is again an average calculation, right? So I need to see the calculation, but that's where the number should go. If your chart looks something like that, you're probably on the right track. I put that chart on my website as well, so you can look at it anytime, unless you really desperately want to take a picture of it with your phone right now. Something like that, okay, will work. Just remember to show all of your calculations in your lab report. All right, because I am going to be looking at that when I mark it. Everybody clear on that one? Another thing to be mindful of. A few people have already looked at how much potential energy versus how much kinetic energy they had, and they're getting a little concerned that the kinetic energy is like way less than the potential. It is what it is. Okay? This is not an efficient energy conversion. All right? If you got a number that was really close, good for you. You did, you know, either, well, maybe you messed up, but maybe you just had a really good conversion. Okay? If your number's way off, like it only seems like it's maybe 10%. Okay? Does it make noise? Okay? Does it, you know, is there slippage like when you let that thing go? Maybe it didn't, maybe the wheels didn't spin, maybe it slid first. Okay? All of those things can lead to inefficiency of energy conversions. All right? So things to think about when you're looking at your numbers. Don't just assume your numbers are wrong. Try and figure out why they are that way. That's part of the lab. Explain why your numbers are different or why they're close. Okay? There's not really a right or wrong for that. Yeah. No. You don't use your force. That's for potential energy. Okay? The kinetic energy is calculated by using the mass of the cart times the acceleration you calculated here times the average distance traveled. Okay? You find acceleration using the formula they showed you on the first page. Okay? Right here. Acceleration of the cart. To use the formula 2d over t squared. Okay? That's why it's not working for you. All right? Any other questions on that, guys? Due date, December 19th. All right, so priority this week and weekend is your unit exam on Monday. All right, make sure you're studying for that. I'll tweet tomorrow's quiz at some point today as well. It's on conservation of energy. Yes.